Hello all, I'm Sahil Sawant. I'm a student at College of Engineering Pune. I'm currently doing my Masters in Technology and I'm here to give a presentation on finding uh, on my paper titled Finding Optimal Path for Gas Pipeline using GIS and RS. So the flow of this presentation is as such. First we're going to talk about the problem statement, then about the framework of the paper, and then we're going to discuss about data collection and pre-processing of the data of the data set. Then we are going to talk about the results of land core classification, and then about the priority and ranking of factors and sub-factors which influence the path generation. Then we are going to talk about generating the path, and then we are going to see the conclusions that I have come to. Yep. So the problem statement is that we want to create an optimum natural gas pipeline route from Kochi to Kozhikode in Kerala. So the study area around it has a mountainous terrain with dense forest and cloudy weather. It also has a large amount of urban settlement. So the framework of papers can be divided into four parts. So the first part is data collection and pre-processing. The second part is classification of the satellite image according to the land use. The third is of about ranking factors and sub-factors which influence the path generation, and the fourth is about path generation. So the data set that we have used is the first one is Sentinel-2 satellite imagery. So Sentinel-2 has 13 spectral bands of different resolution. The second is the second data set that we have used is uh, digital elevation model from Global 30 arc second elevation, also known as GTOPO 30. And the third one is shapefiles, which we have downloaded from University of Texas. So data collection and pre-processing is a very important step or a stage in GIS projects. So we have to download a lot of satellite images in the form of zip for depending on the study area that we have, and each satellite zip, or which is also known as tile, has several spectral bands. And in sentinels, as I told you earlier, there are 13 spectral bands of varying resolution. So some are of 10 meter per pixel, some are of 20 meter per pixel, and some are of 60 meter per pixel. So we cannot go further unless we have all those spectral bands at a common resolution. So that's why we need a step of resampling. So I have upsampled all the spectral bands to 10 meter per pixel to make sure that we don't lose any information, so that it's a lossless process. Uh, so this zip file that we download before is of size 700 to 1 MB to 1 GB, which is and after resampling, each zip file, each tile actually has a size of about 15 GB, which is a lot more. So we make sure that we only select those spectral bands which we need for our project. So we select those spectral bands which have a highest amount of variation in it, which means it has highest information. So to do that, we use an algorithm called optimum index factor, also known as OIF. So after using OIF, we decided to go with bands 2, 3, 4, 8, 8A, 11, and 12. So after selecting those bands, we have to put them into one single file, which is also known as stacking. So after stacking those spectral bands into one file, so this is done for all the tiles that we had downloaded, and all those tiles afterwards have to be glued together into one single image. So that process is called mosaicing. And after mosaicing, there are some areas which we don't need, which are not in our study area. So for that, we do clipping. We clip the amount of area which is not needed by us. So after doing data collection and pre-processing steps, we get this final. So I got this final resulting image. So as you can see the boundaries of the satellite tiles. So after data collection and pre-processing, we move over to the land cover classification. So this image was classified using a random forest classifier, and the training data set was collected from the image that I have shown before. Uh, so I collected the training data set by labeling certain areas in the previous image, and the overall accuracy that I got was of 98.128495%, and the kappa coefficient of this classification is 0.94, and this is the confusion matrix of the result. So the land was classified into into six parts, into six categories: water, urban area, dense vegetation, agriculture, barren land, and vegetation. And this is a resulting land cover classification image that I have got. As you can see on the coastal side, from where the pipeline is supposed to basically goes, is an urban area along with some patches of agriculture. And on the right side, there are vegetation and dense vegetation areas along with some patches of agriculture area. And apart from land cover, there are some other factors which influence the power generation. Uh, for example, slope, railways, roads, and rivers. Uh, and since land cover is such a important part of it, so these are the sub factors as we have previously discussed: water, dense vegetation, urban area, agriculture, and barren land. And we have also divided the slope into 10 classes using quantile function in ArcGIS. And there is no division of railways, roads, and rivers. So we used an algorithm called analytic hierarchy process to find out the weights of different factors. So land cover has the highest amount of weight, and the reason for that is that the settlement of humans and the dense vegetation and the basically the land cover has a tremendous influence in power generation, uh, because land acquisition is I mean it's the basis of this of carrying out this project. And afterwards, the remaining factors are related to the engineering and maintenance cost that we have to incur. So slope has the highest engineering cost, and so it has the highest weight, and it also has the highest maintenance cost because it's very difficult to pass the natural gas from down to up. And the second part is related to railways, since railway crossings entail some engineering costs along with some bureaucratic hurdles. And afterwards are roads and rivers. So since land cover has uh, such a high weight, along with since there are many sub factors in it, so it's important to discuss the weights of the individual sub factors in land cover. So in this, dense vegetation has the highest weight, since we want to minimize the ecological impact of our project. So after dense vegetation, urban settlement has a highest weightage because it's very difficult to acquire land in urban area. And third part is about water, because it's very difficult to build a pipeline in water bodies. it increases in engineering cost, and the remaining factors have the weights as shown. So, the last part, or the power generation. So as you can see, we start with on the left. So we give an input of digital elevation model that we have clipped to our surface, to our study area, and we give it to a function of slope. So after slope giving, so the output of the slope function is basically a classified image of the digital elevation model, and then we reclassify it to 10 classes, because the classes that we get from slope are more or less. So the output of the reclassify is reclass slope or reclassified slope. Along with reclass slope, we give more input to this weighted overlay function. We give roads, railways, and rivers as in a shapefile format, and the reclassified land cover image to weighted overlay function. So weighted overlay basically combines all this with the weights that we had got previously by using HP, and we get output raster, also known which I have named weighted overlay. So this output raster is given to a cost distance function along with the destination that we want to reach. So the cost distance function basically outputs a cost distance raster and a backlink raster to give the direction. So both of these are combined together along with origin to generate a cost path. So the output of the cost path is a shapefile which denotes the path that we have, the resulting path. So this model was run in ArcGIS, and this is the result. So I ran it on 3 times, and these are the 3 paths that we have got. So as you can see, they are colored in pink, yellow, and blue. It starts from the bottom at the red dot up to the green dot at the top, and this is the path. And here is the same path shown by using the shape files of railways, roads, and the rivers. And so these are the results of this paper. And the conclusion, as you can see, is that it's physically, it's topologically impossible to reduce the number of crossings on the railways uh, on any in those between those 2 points. So all of them have the same crossings. So there is some leeway in roads. So the third path has the lowest amount of road crossings, but it has the highest amount of river crossing. And so these are the results. And the distance of the second path is the lowest of 182.10 kilometers, and the third path has the highest uh, distance. So these are the results, and thank you for your time.